Yesterday's class we quickly looked at what happens when you have a DC gain error, right? Primarily the ways to increase it were change the current, decrease the current, which you don't want to do because it changes the unity gain frequency, correct? Which is GM, because if you reduce current, you reduce GM by C. The other option is to increase the length. Again, you don't want to do this because it increases the capacitance, right? So now you are moving in parasitic poles. What is the third option we looked at was to add a current control current source, which boosts the output impedance. Okay, in the example is a cascode, okay, a common gate structure. And the fourth case was adding a current control voltage source, which was another GM stage, correct? And now we also said that, for example, so this is an example of a two-stage op amp. Okay, so you have two transconductance stages. Okay, now if you make the, let's say, the second stage into a more complex stage, like here below, you can get a three-stage op amp. But more than 3 stages is very, very uncommon. Okay, because now you have lots of nodes. Each node has a parasitic pole, so you have a problem. You'll have a problem with the with your phase margin. Okay. Okay, so let's quickly redraw that again. We'll just redraw the two-stage. Okay, so apart from the C, so now the difference between this and the earlier case is that now C is actually put across the input output of the second transconductor to act as the integrator, to act as I to V converter. Okay, and also note the signs. I have been putting all the signs, plus minus signs, but right, what you need an overall negative feedback, so you know what the signs should be. So just keep track of that. Okay, so now if you had to write the transfer function of this, okay, I want you to calculate out the overall transfer function as a homework, okay, but if you just had to write it down, if you just had to think about what terms it would have, so what will be the DC gain? So normally whenever you write a transfer function, you want to write it of the form DC gain times some fraction, numerator has all the zeros, denominator has all the poles, right? That's the way we have been writing it always, because that makes it very easy for us to understand. Okay, so what is the DC gain of this? Very simple. GM1 times GM2 RO2. Okay, that is your DC gain. Is it going to have any zeros? Okay, what is the approximate position of the zero? Approximately GM2 by C. So right now, so I'll say omega Z is approximately GM2 by C, but you will calculate the exact value. It probably is going to be very close to this. Okay, how many poles does the system have? Why only 2? I see 3 capacitors there. Correct? So these two, because you have 3 capacitors in a loop, right, and there are only 2 state variables actually, right, because you can't have independent voltages, right? Okay, 2 poles, so I'll just write them right now. Write it as S squared plus S type something plus some constant, or in this case plus 1 is also, this is where we want to write it. Okay, so I want you to go back home and calculate out the actual exact expression. It's a fairly simple system. Okay, I want you to calculate the transfer function, 0 poles. Okay? Actually, looking at it, where do you think the poles are going to be? Can you say approximately where it's going to be? C1 plus C2 times, yeah, probably, yeah, it's going to have the gain of this, it's going to act like a Miller capacitance. The gain of the stage is approximately GM2RO2. It's going to look like that times the capacitance plus C1. Okay, so that is going to be the capacitance associated with the pole. The resistance is just going to be RO1, right? Similarly, at the output, what do you get? C2 plus C times RO2, right? So those are the approximate positions. Okay, anyways, you'll calculate it at home. Okay, maybe next class. I don't think we'll have time to get to it today, but maybe next class we'll start analyzing this structure. Okay, because I don't want to do all the algebra, so it will just take unnecessary time. Okay, if you have a case like this, actually, the relative positions of the poles, what do you think it's going to look like? No, you gave me the relative, the two pole positions, approximate positions. Are they going to be very close, very far apart, somewhat far apart? Far apart. Because in one case, you have the Miller cap, the other case you don't, right? That's the whole idea. Okay? If you have a case like that, so those are the two poles, right? In the denominator. So if you have two poles, there are some easy ways to, so this is actually a quadratic. So if you want to separate the two poles, there are some easy ways to approximate the pole positions, right? Because one root is going to be very small, other root is going to be very large. So if your quadratic equation is ax square plus bx plus c, right? If x is very small, which is one root, then you can neglect x squared term, and one root can be approximated to be minus c by b, right? If x is very large, then you can neglect c, so it will be minus b by a. Okay, so that is an approximate solution. We'll do that tomorrow anyway. So we'll apply that here, because you don't have to, because when you calculate out, you probably won't be splitting, separating out the poles. You will just calculate the transfer function from input to output, and you will get a quadratic in the denominator. Okay, because we'll calculate the approximate locations. But anyways, let's come back to the iconic architecture we came up with. So you have a GM, you have RO, you have C, gain of 1, this is your VO. Right? This is the op-amp architecture, right? From a very, very high level we came up with. Why did we need this buffer? Finite loading, right? For example, if I take this op-amp, if I put into something like this, let us say this was your original integrator. Okay, what is it going to look like now? So this is the ideal integrator. So we saw yesterday, what is this value? This is the case without any feedback. Okay, the red one is the case without any feedback. What is that going to look like? What is the DC gain? Gm by G0. Correct? Okay, so just to distinguish, I'll make this blue. Now if I put it into feedback like this, what is the new DC gain? What is the new DC gain? you're going to get RO in parallel with the resistance, right? So the DC gain is going to reduce a lot. So you'll actually get something like this. Okay? So primarily, here you can't use, if you remove the buffer, okay, so we are talking about the case where you get rid of the buffer. Okay? If you remove the buffer, you know that your DC gain is going to drop. So if you put it in a case like this, or even if you have any kind of resistive load for this op amp, correct? Any kind of resistive load you have for this op amp, you are going to reduce that DC gain. Is that clear to everyone? So you definitely don't want that. Okay? Now suppose you take the same guy. So let's say I apply it without the buffer. Okay, so this is no buffer. Okay? And I try to drive a capacitance, CL. What will happen? First of all, what's omega U? What is omega U? GM by C plus CL. Correct? Is that right? Inside the op amp you have one C. It used to be GM over C, but now you have a CL, so it's GM over CL. Okay? What is the DC gain? It's the same. GM by G naught. Correct? So this kind of, if you don't have a buffer, there is no problem driving a capacitive load. There is no major problem. Of course your omega U changes, but you don't have any change in DC gain. Okay? So what does this mean? So this means that your steady state error doesn't change. Okay? So unless you have a very, very large capacitance, you will be able to handle this a single stage op amp. This is a single stage op amp, right? This will be able to handle a capacitive load. Correct? Okay. And this is your, so I'll call this V1, V2. Okay? So now if you had to come up with an architecture for this GM stage, what would it look like? Just the GM stage alone. So note that you have two inputs, V1 and V2. Correct? So you definitely need two inputs, right? So natural place to start would be a differential amplifier. Let's call this I0. Okay? What are the output currents? So I'll assume you first need the common modes at the inputs. So VCM plus or minus VID by 2. What are the two output currents? Minus GM VD by 2. Those are the two currents. Okay, but we are still not at a point where we have a single output current. So if you want a single output current, what do? You have studied this before. Loudly please. No, I know we want a single-ended output. How do you achieve it? So you have the input. So input, you have achieved the difference in the voltages. You convert into a difference in currents. Okay, but now, of course, one easy way is to just discard one side and just take the other side, right? But that's obviously not optimum. It's not optimal. You can use a current mirror load. You have studied this before, right? Okay. Okay. So what is the? So we know what these two currents are. What is the output current? GM VID. Correct? So you have GM VID by 2 flowing through this. What is this current? GM VID by 2. And so you have minus GM VID by 2 flowing like this. So you have GM VID by 2 flowing upwards. So which means that the total output current is GM VID. Okay? Okay? What is your omega U? So let us say, I'm going to add a capacitance C here. Okay? What is omega U? Omega U is just GM by C, right? Right? Because the overall transconductance is GM, the capacitance is C, so omega U is GM by C. Okay, it's recording. What is the DC gain of this? GM by GDS2 plus GDS4. Okay? Is that clear? You have you had problems with regarding, with respect to these kind of stages? Any calculations, numerical calculations? No. What do you think the typical gain you are going to get from this, the DC gain? You've actually seen, right, how when we looked at the output impedance, the GM and so on, GMBS output impedance, we saw the relative levels. What were the relative levels? Typically, GDS to GMBS to GM was approximately 1:10 to 100. Those are the order of magnitude. Correct? So the gain you can expect from this kind of stage is probably few tens to maybe 100 to 200. Not much more than that. Okay? Okay? What is this GM? What is the value of that? Just remember that. Okay? So it's actually I naught by 2 because we are talking about the GM of each device. Okay, don't use I naught. Okay? Now, let us say, let me use a different color. So now I'm going to call this node P and I'm going to call this node T. Okay. So you have, so let's say now I want to start drawing the parasitic poles in the system. Okay. Definitely you have one at the current mirror, at the current source node, which is P. So you have CT there. What else do you have? You have CP and what else? Anything else? Yes? To a large extent these two, because if you have, you'll have one at the output nodes, the drain bulk capacitances, but those you can lump into C. Okay, C is probably going to be large enough. Okay. Now, what is the effect of CT? Sorry? So, is this circuit differential? Is this circuit actually differential? It is not, okay, because the two sides are not symmetrical, okay. But you can, for the purposes of, as long as you assume that the output impedances are large enough, right? If you apply VID here, and the second condition is there is no mismatch between the transistors. If you apply VID here between these two, this node will be a virtual ground to a large extent, okay. So even though the circuit is not purely differential, you know that VT is going to be approximately 0, okay. So you can neglect the effects of CT, okay, to a large extent. Obviously if you have mismatch and so on, that changes, but to a large extent you can neglect the effects of CT, okay. How about CP? How about CP? What is the pole at that point? First of all, what is the order of the system? Now, let's go back to the picture, sorry. What is the order of the system? It's second order because we have assumed that CT is not going to bother us. Okay, so it's a second order. Okay, how many poles and how many zeros does it have? 2 poles. Okay, so you have 2 nodes, 2 capacitances, 2 poles. Okay, does it have a zero? Actually, we discussed this in class, didn't we? A few weeks ago we did. Okay, so anytime when you have 2 paths to the output and you have a phase shift between the different paths, you will have a zero. Correct? We saw that. So this side, definitely what are the 2 paths? One goes like this, the other goes like this, and this side definitely has an extra phase shift. Correct? So you are going to have a zero. Okay? Okay, so what is the approximate position? Actually, can you write down the transfer function without at least the poles by looking at the picture? What is the, where is the output pole going to be at? Output pole is going to be at G out by C. Okay, so you are definitely going to have something like this. Okay, what is the second one? GM3 by CP, correct? Okay. This is going to be the approximate pole locations. Okay. Now, if you assume G out is small enough, remember we are trying to achieve an op-amp with very large R out, which is very small G out, and we are actually, remember, we are actually trying to make an integrator. So ideally what you want is something like this, remember? Correct? So ideally you want GM over, let me call it GM1 over G out, this is the DC gain, times this some zero you have, and over some pole, right? But now what you actually want is this. So if you cancel out these two, what you want is actually GM1 over C, that is your integrator which you want to achieve, correct? Times something by, you'll have S into 1 plus SCP over GM3, okay? That is what you want to achieve, correct? Okay. What is the frequency of omega Z? What is the zero? I think I asked you a long time ago to calculate this out, right? Go and read the chapter and calculate it out. Did anybody do it at that time? This was when we were discussing at a higher level, when you have zeros and so on. I think I gave this exact same example, didn't I? Okay, so anyways, then why don't you go ahead and do it today? Okay, I want you to tell me tomorrow. Okay. Or okay, anyways, I want you to confirm. We'll go ahead with the class. I want you to calculate it out and confirm whatever we are going to do now. Okay. So if I just take these two portions over, I have one pole and one zero apart from the integrator. Okay. If I just plot the gain of this, what should it look like? Actually, if you just look at the circuit, what is the gain at what is the gain at very high frequencies? What is that GM at very high frequencies? That is another way to find out, right? What the zero location, what the pole location should be. What is the effective transconductance at very high frequencies? What happens to the current from M2? Anybody? So the current from M2 has no problem. Minus GM VID over 2 is going to flow like this. What happens to the current from M1? All of it is going to flow like this through the capacitance. So your actual transconductance at very large, very high frequencies is actually going to be GM1 over 2. Okay, that is quite often a way to find out what your where your zero should be and where your pole should be. Okay. First of all, to tell you that there is a zero, because now you know that the gain is actually changing as a function of frequency. Correct? That itself should tell you that there is a pole and there is a zero. So if you just plot this, it looks something like this. At very low frequencies, the ratio is just 1. Remember, you are looking at 1 plus omega over omega z over 1 plus omega over omega p. At very low frequencies, this portion is just going to be 1. Okay. At very high frequencies, what is it? It turns out it's going to be half. Okay. Because in this case, the pole lies at and this one happens to lie at 2 GM3 over Cp. In this case, the 0 happens to come at 2 GM3 over Cp. Okay, I want you to go and confirm this today, at least now. Okay. And how do you decide if it's a left half plane or a right half plane 0? Can you tell just based on this whether which one it is? You can't. You have to look at the phase shift, right? Okay. Anyway, I want you to go and tell me tomorrow whether it's a LHP or an RHP 0. It's a very simple circuit. Okay. This is what you get for the overall transfer function. So to calculate this out, we have basically completely neglected GDS, right? Obviously we assume GDS is very small. That's when you'll get this. If you want to add GDS, then you know that to SC you're going to have to add G out. Correct? So the actual expression will be GM1 over SC plus G out. Correct? And then what do you have here? Here it will be approximately the same because you will have GM1 plus this thing, right? Something. In one case you neglected G out plus SC plus G out, you neglected G out. So if you put that back in, you will get the right expression. In the other case, GM plus GDS, it's a perfectly good approximation to call it GM. Okay, so here the pole positions won't move much. Yes. In fact, that itself, yes, that's right. And that itself tells you that there should be a 0. Actually, first of all, that tells you there should be a 0. Right? Okay. Now, the value of the gain will tell you where the pole, anyway, think about it. Okay, we'll discuss it next class. I want you people to think about what it means. Let's say you found out the value of the 0 and value of the pole. Right? Look at the transfer function. Write it as 1 plus S over omega Z over 1 plus S over omega P. Right? Take a system with a 1, 0 and 1 pole. Okay. Suppose you know the gain at low frequencies and high frequencies. Think about how you would find out, and think about how you would find out the 0 location if you know the pole location. Okay. And tell me tomorrow, of course, right? Okay. So that is the transfer function of this. What is CP going to consist of? CdB of M1, okay. Plus, oh sorry, did he say CdB? Plus, okay. Anything else? Forget CGDs for now. The gate to drain capacitance, we'll forget about it for now. It's usually very small. CGS of 3. Anything else? Drain source. What drain source? There is no drain source capacitance, right? Okay. What else? Anything else? Huh? CGS of 4. Correct. Okay. So these are the 4 capacitance you are going to have. Okay. And that is will tell you it's probably going to be an important pole, because now you have 2 gate source capacitances. Gate source capacitance is the largest capacitance, right? 2/3 WLC ox. Right? All the others were either junction capacitances, or maybe CGD was overlap capacitance, which is even smaller. Okay. Okay. So now suppose we want to look at the stability of this system. So this is the magnitude, this is the phase. Okay. What is the magnitude going to look like? Something like this. This is ideal, right? This is what you want, GM1 over C, right? You want a single pole, GM1 over C. With the parasitic capacitance, the DC gain did not change, correct? So let's say you go down this. Okay, you can actually look at two cases. One where, so now you need to compare GM1 over C with GM3 over CP. Correct? Those are the two poles you have. Okay. What do you want? Ideally you want this. Correct? And if you have that, you'll have here, you'll hit the second pole. I think I gave you the, remember that this is your 0. This is your pole. So you first hit the second pole, then eventually you'll hit the second 0. So now it will start going at 20 dB per decade again. Okay, is that clear? Okay. What happens if this condition is not true? Let us say was of the same order as GM3 over CP. What happens? Let's say just a little bit larger, or let's say even smaller. What you'll get is the DC gain again won't change. It will do this. Let us say you hit the second pole here. It may do something like this. Correct? And this is still 20 dB per decade. Is this stable? Actually, can you tell that it's whether it's stable or not? How do you know it's not stable? Huh? Exactly. First of all, it depends on whether it's an RHV0 or an LHV0. Okay. Second thing, you can show that is as far as the phase is concerned. As long as it's the right kind, you can show that if you can draw the Nyquist plot. Okay, so I want you to draw the Nyquist plot. I think we'll have it in the tutorial anyways. But you can show that if a system crosses, the magnitude plot crosses the 0 dB value at 20 dB per decade, you can show that the system is going to be stable. Okay, and you will see that the Nyquist plot will work out correctly also. Okay. We'll just take it for granted for now. Okay. And if you plot the phase for this guy, so you first hit the first pole, second 0. In this case, it happens to be something like this. Okay. You hit the second pole, and then you hit the 0, and it. Okay. Actually, first of all, in this case, we are just assuming, we are just comparing GM1 over C with GM3 over CP. If you have a feedback factor of K, what happens? Okay, you have a feedback factor of K, then you want to make sure GM1 over CP is much larger than, sorry, GM3 over Cp is much larger than GM1 over C over 1 over K. Okay? Okay, so let's say you want to get this condition. So normally you don't want this anyways. Okay, first of all, even this is stable, but you don't want this because you are basically pulling in your unity gain frequency unnecessarily. Okay, so you want to make sure that this condition is satisfied. How do you satisfy the condition? So what do you want? You want GM3 by Cp. This is what you want. Okay. What are the ways to make sure this happens? Increase C. Okay. Definitely increasing C is an option. But what is the problem with this? Bandwidth, right? You're trying to achieve a bandwidth unity gain omega u of Gm over C. So you're going to affect your bandwidth. Okay. What else can you do? Okay. Increase GM3. Okay. So let us say you want to make it GM3. How do you increase GM3? So let us say if you increase the current, what happens? What happens if you increase the current? GM1 also goes up, right? So increasing current is not an option. This is definitely not an option. What else? W by L. So let us say we increase the W over L. What happens? Cp also? Okay. Cp also increases. Okay. So what can you do? Increase? Exactly. So the only thing we can do is actually increase the current and decrease W over L1. So if you do this, by increasing current, you are increasing GM3, but by decreasing W over L of 1, you are keeping GM1 constant. So you are basically moving them apart. Correct? So that is the only way to do it. So in other words, this has two effects. You are burning more power. So, okay, that is one fundamental thing you have to realize. Okay, you are burning more power because you want to maintain speed. So that is directly the speed power trade-off. Okay, what else does this do? As he said, VGS minus VT increases. So now you are hitting headroom problems. So in other words, you are limiting swing. Okay. Okay. So that's it as far as so this is a fundamental trade-off you'll see in almost every op-amp you do is this power versus speed trade-off. Okay. So now let's go back to your single stage op-amp, top level. Okay. So this is single stage Diff pair. Okay, that is your Diff pair. Can you do anything else? Let's go back to one of the other techniques we discussed. What was that? How do you? So now we know we want to increase R out. What is the other way to increase R out? Cascode. Okay. So if you make this a cascode, cascode stage. So let's say this is GM. What is the transconductance here? So all I am doing, I had the diff pair, I am adding a cascode to the diff pair. What is the GM? I am adding a cascode devices to the diff pair. What is the GM? New transconductance. It's the same, right? What is the new R out? Some GM R naught times, I'll call it RDS, okay, some GM R naught times RDS, so it's basically much greater than R naught, okay. So what is the omega U? What is the new omega U prime? It's the same as before, right? Right? What is the new DC gain? Now it is, of course, it is basically GM R naught prime, which is basically much larger. Okay? Okay? Okay, so now you have increased your DC gain a lot. Suppose I add a resistor in parallel with, I drive a resistive load. Okay? How does this perform? Is it fine or does it have the same problems? Same problems. No, it won't be fine. Because if you drive resistive loads, your gain is actually GM R naught prime parallel RL. Correct. The fundamental problem, if you even take the single stage op amp, you drive RL, so your actual DC gain becomes GM R naught parallel RL. R naught is, you are trying to make R naught large, so in other words, it will just become approximately equal to GM RL. The other case, you have just made R naught prime even worse, so you are going to be again even higher. So you are going to be at the same GM RL. Correct? So again, you can't drive resistive loads. Is that clear? You have to tell me, why did we do that? Why did we care about DC gain? Actually, I mean, that's what we have been discussing the last two classes, right? Why? Huh? Okay, I think you should go back and read what we have studied for the last classes. I mean, I thought we started off from there last class and then came back, right? Okay. Anyways, yeah, I think you should study regularly. Okay? So this is just a cascode op amp. Okay, just a single stage. Same thing, you have the diff pair, you had a cascode for the NMOS, cascode for the PMOS. Right? Because you want to increase the output impedance. Correct? So it looks something like this. So I'll So if you just add the cascode for the NMOS alone, you will increase the output impedance of the lower half but not the upper half, right? So earlier you had GDS2 plus GDS4. right? If you just add the cascode for the lower half alone, then you will basically get GDS4 will reduce a lot, but GDS2 will still be there. Correct? So now you need to make the upper side also a cascode. What will you do? How will you make it a cascode? What kind of cascode will you use here? You can use a high swing cascode. Okay, nowadays obviously with small supplies, you would use a high swing cascode. Okay. What is VB1? Okay. And this is your output. Actually, before we go any further, let's go back to this guy. What is the noise performance of this op-amp, of the single stage op-amp? What is the noise, output noise? Let's say the output noise, output current noise. Okay. Well, where does it come from? M1 squared. I can see how you get M2 squared. How do you get M1 squared? I mean noise from M1. Go through the current mirror and go to the output. Right? Perfectly fine. Okay. So you get noise current from M1 and M2. Anything else? How about M3 and M4? How about M3 and M4? Will they contribute any noise at all? Okay. Okay. So, if I want to calculate my noise current, so let us say, so okay, you can look at it in multiple ways. Normally what do you do? If you want to calculate the noise, if you usually want to refer it, use it, measure the noise performance using the input referred noise. What did we do for that? We shorted the output, calculated the output noise current, divided by the, right? Isn't that what we did? Or you can calculate it, you can find the open loop voltage and divide it by the voltage gain. Either one is fine. Okay? So let us say we short it. What is it going to look like? So you short it, find out the current and divide it by transconductance. Right? Suppose you short this and find out the current through that short circuit. What is it going to look like? What components is it going to have? M1, M2. You guys just said it. I'll accept it. What about M3, M4? M4 will have, definitely. Okay. What about M3? No? It won't have? It won't have? Okay, I think you should go back and study the noise performance of a current mirror. We discussed this exactly in class. We discussed the current mirror and found that at the output of the current mirror you will get noise from both this and these sources, right? Let me see if I can pull it out. We are running out of time, but let me see if I can pull it out. I remember doing it in class, that's why. We discussed this when we did this, right? Did we talk about this in class? We did a current mirror biasing a common source in this case, or a common gate in this case, right? We discussed the noise. We said that both M3 and M2 will appear at the output. We talked about what happens when you add a capacitance. Or if you add a capacitance, then M3 noise goes away and you get only M2 noise. Remember this? Right? Okay. So in other words, In other words, if you look at the overall noise of this op amp, you're going to get noise from M1, M2, M3, M4. Okay? What about the current source? I naught. Are you going to get noise from, let's say this is just a normal transistor M5. Okay, it's just a current source, current mirror. Will you get noise from that? Yes? We discussed this also. I want you to go back and look at your notes. Okay? Does anybody remember? Exactly. We discussed this also. It'll be like a common mode. Okay? The case we discussed was for a resistive load. I want you to go back through the mirror and see if it really cancels out. Okay? Just do it as a homework. Okay?